Okay, so welcome everyone to today's webinar. So today we have in the first part the presentation by Daniel Voss. So it's my pleasure to introduce him to you and welcome him in row. So Daniel is currently a postdoc at Technical University of Delft in Algorithmic Group. He has been, and then he also submitted his thesis, a PhD at the same university, but in the group of cybersecurity. And his work is aiming at making machine learning models more trustworthy by combining different optimization problems and approaches together. And here he's going to talk about robust optimal classification trees. So without further ado, Daniel, the control of the mic and screen is yours.
Yeah. So first of all, thanks for the invitation. I'm very happy that I could be here a second time after getting sick last time. And as a warning, I guess, to all future speakers is I'm sick again. So there might be a causal relation between getting invited to be a row speaker and getting sick. But that's to find out in future episodes, I guess. Um, yeah, I wanted to start with this example. And I guess we cannot do a lot of interaction on Zoom, but we can try. So I put two images on the screen, and I would like you to guess what a neural network would see in these images. What would a neural network classify these traffic signs as? Um, I can give a small hint. Only one of these two is a stop sign.
Maybe the right one is a gibbon.
Good guess. Yeah, so you've seen this kind of image before. Now, in this case, the right sign is classified as a maximum speed 100 sign, which you can imagine is quite problematic. If you truly have a sensor built into your self-driving car that misclassifies a sign like this, you could get into a lot of trouble. And what is actually the difference between these two pictures is that the picture on the right is similar to the one on the left, but each picture has been, each pixel inside this picture has been shifted by a few values to make every pixel slightly different. So very carefully crafted noise is added on top of the image, and this is enough for the neural network to completely misclassify it. Now, if you've been in this field, you might know this already, and you have probably um, seen a lot of work trying to fix this for neural networks. What I've been doing in my research is to try to fix this for another class of machine learning models called decision trees. So decision trees are usually valued over neural networks when you require the model to be interpretable. And I put a very simple decision tree on this slide that could be used, for example, to classify credit card fraud. Now, I should mention this is overly simplistic, but the idea is clear. We get a very simple set of rules that we can use to make predictions. For example, we see that if you have made transactions in more than 2 different cities in the last 24 hours, and the number of transactions was larger than 4, you might have a fraudulent credit card. So the value of decision trees is in trying to exactly understand what the model is doing. Unfortunately, these things are not robust by default. And I'd like to demonstrate it like this. So consider a very simple data set where we have red dots and blue dots, and we're trying to classify them with a decision tree. We could make a very simple split in the middle and get an 80% accurate model. The problem is, though, that if we if we move each of these dots by a small amount, we get 0% accuracy. So if some adversary has control over these dots, this is a very bad model. What we will try to do in this work is to train robust models that might trade a bit of accuracy for robustness. For example, in this case, we have a 70% accurate model, but if you account for changes of these dots within the squares that I drew around them, you can be sure that you don't lose any performance. So this model is 70% accurate against adversarial perturbations within this defined radius. And what this looks like in slightly more real data is something as follows. So we have clouds of now minuses and pluses that we want to separate. Typical decision tree learners will often learn a very thin strip. It's a small bug basically inside the model, and this would allow a lot of small perturbations. So what robust models would do is try to avoid making these tiny regions in the prediction space. And mathematically, what it looks like is as follows. So in normal learning, you've probably seen this many times before. We minimize a loss by changing our model parameters such that the expected loss for our samples and labels is low. In the robust optimization setting, we add an adversary within the minimization term that tries to maximize the loss by adding a perturbation from a certain domain. And in our work, this domain is a ball of L infinity norm around 0, basically. So effectively, that is a square or a box in higher dimensions around your data points. In decision trees, this is very useful because decision trees make straight splits aligned with the axis. So therefore, an L infinity norm very naturally captures these kind of similar splits. Okay. So before we go into the work that I've done, I think it's good to first discuss how people have trained these models before using greedy methods. So normal heuristic decision trees that people use every day are trained as follows. You try every possible split through your data set. You score each of these splits according to some score function. In this case, it's the Gini impurity. Doesn't really matter how it works, but low values are better. Then you choose the lowest value, you make the split, and you just keep doing this on the different sides of the split. You just keep growing your tree. There's also a few robust heuristic decision tree learning algorithms. What they do is they encode a certain radius around each sample in which we can expect perturbations. Now we will try twice the number of possible splits because we need to try the maximum ranges of each sample's perturbation. And we will score them, but this time not with the Gini impurity, like I said before, but with a maximized impurity. Effectively, what that means is, in this case, there are two samples that are close to the split. So we need to consider all the different kinds of perturbations that we could do to place the sample on the different side of the split. If we would move the red point to the left side, we get a score of 0.48. If we do nothing, 0.42. Blue to the right, 0.48. And if we swap both samples, we get the worst possible score of 0.5. So in these robust heuristics, we say that this is a very bad split because it has a weighted Gini impurity of 0.5 after perturbations. And what we've done, so this is work from my master's thesis, before was trying to make these robust heuristics a lot faster. And we did that by, in closed form, computing these worst case perturbations. So it's good to know that there's very fast heuristics for robust trees, but they're not perfect. They work similarly to the other greedy methods. The problem, though, is that they don't have any guarantee. So here's a data set where we have XOR-shaped data. We have two classes, one on top left and bottom right, another class on the bottom left and top right. And all these greedy decision tree learners will train the model on the left side. So they will just predict the same class everywhere, whereas an optimal tree could easily learn the model on the right side. And this is the case because when you only consider one split at a time, you can never make any improvement on your classification. So you need to consider multiple splits at the same time to get the optimal model. And yeah, this motivates, of course, research into optimal decision trees. I'm assuming that a lot of people here have probably heard of the name Bertsimas. And so first, it might be good to look at his work. There's a paper called Optimal Classification Trees, which very nicely illustrates how you can train optimal decision trees for the normal case, the non-robust case. Basically, the idea is to fix the structure of your decision tree and use these variables A and B to decide the predicates that are used to decide which side of the tree you're going to as a sample. So what I mean by that is that if we input a sample in the top, if its feature value is less than B, the threshold value goes to the left, otherwise it goes to the right. And what Bertsimas's formulation does is trying to set the variables z, I, meaning sample I reaches leaf number 6 or reaches leaf number 7. Basically, when you can encode in terms of constraints what leaf your sample will fall into, it's quite easy to construct the rest of the formulation. And how they model these branch nodes is through variables A and B. Sorry, by the way, I'm just sketching this idea. It's not very important to know the exact details, but we have variables that decide which feature to use, and we have variables B to decide what threshold value we're going to use. And they use these constraints, which essentially force leaves to 0 if a sample follows a certain path, and otherwise do not constrain the Z. Yeah. So what this looks like is if I have a sample that can go into the right side of the tree, we know for sure that it can never reach the left side. So we will set all these Z variables to 0. I'm not going to go into any more detail about this formulation, but it's important to understand this because this is the difference between the robust and regular optimal decision trees. In the end, Bertsimas has a nice MIP formulation that you can just generate for your data set. You can put it into your favorite solver. You can wait a long time, and then out comes your optimal decision tree. Now, as I hinted to before, this is a bit different in the robust setting. Because in robust trees, the big problem is that your sample doesn't just follow one path through the tree. After accounting for perturbations, you could follow different paths through the tree. And that actually makes using the kind of constraints that Bertsimas's paper used before quite difficult, because we can never, for example, if this sample goes to the left side, we cannot just forget about all the leaves on the right side. It could take a different path through the tree. And so what we've done in our work is to encode the variables z, so in which leaf does my sample end up in. We've encoded these in terms of the paths that the sample takes through the tree, and not by discarding the whole subtrees every time. What we end up with is a single minimization formulation. So where before, in the general problem, you have to minimize your loss as it is maximized by an attacker, we realize that we don't have to consider this potentially infinite sized attack domain. We only have to look for each leaf whether or not this is reachable by the attacker. So we can just enumerate over a fixed number of leaves and encode these into separate constraints. So effectively, this becomes a single minimization problem that we turn into mixed integer programming, and that we can give to a solver. Yeah, we also made a slight change compared to Bertsimas's work, which is that we encoded thresholds not with a continuous variable that can take any value between 0 and 1, but we split up the space with separate binary variables. This might be too detailed, but this basically avoids some numerical issues. And I've created a small example to, at a high level, I guess, understand what the formulation is doing. We have all these threshold values that I told you about before that we enforce to be sorted from 0 to 1. And we say there's the threshold is placed at the point where the 0 is changed to the 1. So in this case, the green threshold is the one that's selected by the setting of the variables at this point in the solver. And we have variables A still to decide in which feature we put the threshold. Now we have 3 samples on the in the plane here, and we can see how they will move through the tree. So we have a sample A whose class is 0. It can only go to the left side of the threshold. The class label predicted in this leaf is 0. Since that's the correct label, sample A is predicted correctly. B can take 2 different paths through the tree, and in the left leaf, it is mispredicted, while in the right leaf, it's correctly predicted. Since one of these 2 leaves mispredicts the sample, we count the sample as mispredicted. And on the right side, we have a sample C that will always go to the right side where it's correctly predicted. So we consider this sample correctly predicted. Basically, your sample is mispredicted whenever an adversary could change it in such a way that it reaches a leaf with the wrong label. In the end, we have a MIP formulation that we can give to Eurobi, for example. We also experimented with MaxSat solvers. Since I'm from the computer science field, this is maybe dangerous to say here, but we also experimented with that. And if you wait long enough, of course, you get your optimal decision tree. The rest of this presentation is about evaluating this method. We try to figure out how it compares to the heuristics that we saw before. But before we dive too deep into that, I think it's important to talk about how we evaluate this problem, because just like in the rest of robust optimization, an important consideration is how you choose your uncertainty set. And this actually matters a lot in this case. So what we realized is we need to be smart about the size of the uncertainty set that we consider. It's very easy to choose a value that's too small or too large. And for this, we computed a general upper bound on adversarial accuracy for a given size of the box that surrounds each sample. The trick is to look at every pair of samples and create a graph where we connect them if they have a different label, but they can reach any same point in space. So for example, this blue sample and this yellow sample can reach the same point in space, and that's why we'll connect them in the graph. What it means is that these 2 samples cannot be correctly predicted at the same time. There's no possible model that ever gets 2 correct, because if we predict blue in this area, we can move the yellow point into it. If we predict yellow in this area, we can move the blue point into it. So what we do is we create a graph, and then we find the maximum bipartite matching, which basically means what is the size of the matching is the minimum number of samples that we have to mispredict in order to be able to correctly predict all the other samples. And so this gives us an upper bound on the adversarial accuracy that any machine learning model could achieve on this data set. We then looked at these kind of plots at which we vary on the x-axis epsilon, which is the size of the uncertainty set. And on the y-axis, it's the value of the bound. And they usually follow this kind of curve. What it means is at the start, at low values of epsilon, we will be able to score 100% accuracy. But this is not super interesting because this is actually the same as a non-robust setting. Then all the way on the right, for large epsilon values, there's also a problem because there's a trivial solution there, which is just always predicting the majority class. You will always get, for example, 60% accuracy if your data set has 60% class 1 samples and 40% class 0 samples. So the interesting part is actually the part in between. And this is what it actually looks like for various data sets. What was interesting here is that some of the epsilon values that previous works have used either fall into this trivial region at the end or fall into the trivial region at the start. So it turns out that some previous evaluations, also evaluations that I had done in my master thesis, were actually not so interesting after all. In this work specifically, we then took points along this curve that we hoped would be non-trivial. And then we ran, of course, all the algorithms on various settings on various data sets. This is 30 minutes of runtime for 8 different data sets and 3 different epsilon settings per data set, and then the aggregated results. Treant and Groot are existing robust heuristics. They performed quite well in our experiment. And then we looked at different kind of solvers that we gave our formulation. So we have MALP solvers. Binary or nothing means either the Bretzi-Mastau continuous threshold formulation or the binary threshold formulation. And MaxSat is, of course, this maximum satisfiability solver, not a MIP solver. Warm start means that we warm started the solver with the Groot greedy solution. So it turns out that to within 30 minutes improve the performance over greedy heuristics with a MIP solver, you basically need to warm start it. But if you do this, you do get better performance. We were surprised, though, to see that this MaxSet solver, which is not typically used in the field, is a very naive method, was actually already better than the greedy solution. And sometimes on specific data sets beat the MIP solver. We looked into this further by looking at the optimization behavior over time. So what we saw, so what we did here is we ran various data sets on a depth-3 tree for 1 hour, and we plotted the percentage training error over various data sets on the y-axis. And as you can see, the purple line is the MaxSet solver, and the other lines are the various flavors of MIP solvers. Somehow this MaxSet solver can find good solutions very quickly. It's just that the MIP solver sometimes had an edge in improving optimality of the solution. And a last thing we checked is, now that we can actually prove optimality on some of these models, how does Groot compare? Well, we found that empirically, on a lot of the data sets, the Groot performance is very close to the optimal performance. And this gives us some trust that at least the greedy algorithms are good. So in summary, we showed how to turn this robust learning problem into a single MIP optimization problem that we can then give to existing solvers. These robust optimal classification trees, they do beat the existing heuristics, but in practice, the performance is quite close. And some limitations is that, of course, these solvers can only handle relatively small data sets. And what allowed for this neat single minimization problem is the fact that we used box-shaped perturbations, but it's more difficult to extend this to a setting with different kinds of perturbations. And in ongoing work, I'm now looking at Wasserstein robustness instead of these independent perturbations for each sample. If you would like to work on this further, all the code for ROCT and also these other heuristics are on GitHub. Thank you for listening. I'm ready to take questions.